Okay, so it's a pleasure to introduce Mike Cates, who will be our speaker today. He's known for his many contributions to statistical mechanics at large and soft matter, from colloids through polymers, liquid crystals, and more recently, many contributions to active matter. He's won too many prizes to list. I'll just list the Dirac Medal, the Maxwell Medal. He's a fellow of the Royal Society, and in 2015, he was appointed the 19th Lucasian Professor of Mathematics at Cambridge. And today he'll tell us about continuum theories of active phase separation.
Thank you very much. And it's a great pleasure to be here. I'm now trying to get this to work. Ah, yes. So firstly, I hope everyone can see the screen. Can you see the cursor?
Yes.
Okay, so because now I can use that as a pointer if I need to. Okay, so I'll talk today about continuum theories of active phase separations. Recent developments in the sense that this field has been going on for a decade or so now. And I know many of you will have heard me speak on similar topics previously, but I hope at least towards the end of the talk, someone has just been annotating my slide. Towards the end of the talk, there'll be some new stuff, which many of you will not have seen already. So here's a list of collaborators, which of course could be extended back into the past. So the most important ones for this particular talk are in bold today. Right, now let me still get this working. Outline, I'll say a little bit about active colloids and microorganisms, the background against which we want to create these theories. And I'll say a bit about time reversal symmetry and how that is broken in these systems, and then move on to the main business, which is addressing what scalar continuum theories should look like. And for those of you who know what Model B is, I'll be mostly talking about extensions of Model B. And how these can be used to describe phase coexistence. I'll talk about a specific aspect of that, though, which is to do with the route to phase coexistence via the Ostwald process, which is a standard pathway to phase separation that I will describe. And in active systems, as we'll see, for some of these active field theories, this process can go into reverse. And this is a very general explanation of quite a widely observed phenomenon in active systems, which is the occurrence of microphase separation in systems whose passive counterpart you would expect to phase separate completely rather than only phase separate up to a certain length scale and then stop. And then the other thing I'd like to talk about, time permitting, is entropy production and how that works in the context of these the field theories that I'll be talking about. And if there's time at the end, I'll try and squeeze in a little bit about hydrodynamic interactions and the coupling to fluid flow that corresponds to active versions of Model H rather than Model B, but we'll see if we get that far. Okay, so it seems like this is how I have to advance the slides at the moment. Okay, so I won't dwell on this, but the idea is that there are many systems in nature and synthetically in which you have particles of a colloidal scale that self-propel one way or another. They consuming fuel all the time and translating that into motion. And that corresponds to a steady state heat production, a constant dissipative motion against the viscosity of the surrounding fluid, for instance. So examples include motile bacteria, but also these autophoretic colloids, where you have a colloidal particle with some kind of asymmetric coating on it that catalyzes a reaction in the bulk fluid, typically hydrogen peroxide, and the combination of that that chemical reaction and the asymmetry of the particle causes it to move in a specific direction. And many of these systems in the lab can be controlled by light. So at the risk of boring you to tears, this is Paul's famous movie. This is a set of these active particles which only self-propel when illuminated, and they're forming these crystallites. You might ask whether this particular system will go all the way to complete phase separation eventually. I'm interested in the more generic question here about systems which do that and those that don't. If you turn off the light, these become ordinary passive particles. You now see the Brownian motion, and you will also notice that there's no phase separation. And that's because these particles are actually repulsive. So it's the propulsive motion of repulsive particles that results in phase separation. So I don't want to spend much of the talk talking about the mechanism of phase separation because I want to talk about these continuum theories. But the basic idea in these particles, you have a persistent Brownian motion. So the particle has a propulsive speed v. This is on in a direction fixed in the body of the particle. So there's a body axis which rotates by Brownian motion with some rotational diffusivity dr. And at any time, there's a unit vector u in the orientation. If you coarse grain that basically worm-like chain of a path, it's easy to calculate its diffusion constant. It's written down here, v squared tau over d, where tau is the rotational or orientational relaxation time, which relates to the diffusion constant as shown. So if you only had one of these particles, its behavior after this coarse graining would actually be the same as a persistent Brownian motion, which is a perfectly ordinary equilibrium system. However, the absence of time reversal symmetry or detailed balance in the microscopic motion of the particle does manifest itself, and it manifests itself when the particle collides with other particles or with external objects. So this is a movie of a asymmetric cog in a bath of motile bacteria, and you will see that it rotates persistently in the same direction. So this is something which would be impossible in an equilibrium system at thermal equilibrium. Manifest violation of time reversal symmetry in the steady state, ultimately attributable to the same thing at the scale of individual trajectories. And here's motility-induced phase separation. So again, this is a simulation, many years old now, of purely repulsive active Brownian particles. So those are the things I defined before, which have a persistent motion with some orientational diffusivity. And you can see that that undergoes a kind of phase separation. And in this particular system, if you wait long enough, it will go all the way to a full bulk coexistence of a vapor and a liquid phase. Although the liquid phase, even in this still picture, you see looks a bit strange. It has some holes in it, and I will come back to that. Next slide. Okay, so very briefly, the physics behind that phenomenon is that the active particles tend to accumulate where they slow down or where they move slowly. They move slowly where they are dense, and this is a positive feedback loop. So this is very well understood microscopically and confirmed by many simulations on, for instance, these hardcore repulsive active Brownian particles, but also other models at the particle level. Experimentally, it seems very clear that that's part of what's happening, but it's complicated by other things happening too. For example, in the colloidal systems with the chemical reactions that I described, there are clearly chemical interactions between one particle and another. The way that a particle surfs its own gradient of reagents and products in order to move allows it to influence the motion of other particles through non-hardcore interactions. And what is found experimentally that in some systems, the phase separation stops at a certain scale, and then you see cluster phases in the steady state. So I don't have movies of that, but a couple of still pictures on the next slide. Yeah, so if you look at the middle picture here, you'll see there are these clumps, and they are dynamical. Particles come in and out of them, and they have a persistent lifetime. They can be a lot bigger than that. So the steady state contains a kind of microphase separation between a vapor and a dense liquid phase. So that was by way of introduction. So the main agenda here then is to address how to model these kinds of phase separation. And I won't be addressing today the issue of the crystallites, but treating this as basically a liquid vapor phase separation problem, which is the one that you see in the active Brownian particle simulations that I showed you a few slides back. So as a reminder then, this is how we deal with continuum theories of phase separation or field theory of phase separation in a conventional passive system. So I'll remind you of that and then say what is the minimal way of extending that to address phase separation in active systems. So we have phi. Phi is a scalar field. It's a composition or density-like variable, and is conventionally, for simplicity, defined to be positive or negative. So you can think of it as the composition relative to some critical density at which phase separation first begins. And it obeys the top equation, which is that it's a conserved quantity because it's a density. So its time derivative is the divergence of a current called J. The important equation is what is the current. And in the units I'm adopting, it's the negative gradient of a chemical potential, mu. There's a mobility m in front of the grad mu term set to 1 here. And then in a system at finite temperature, there's a noise term, which is written as shown. Lambda there is a unit white noise, which is vector noise as it lives in the current equation. And the chemical potential mu is derivable from a free energy functional. And it's conventionally this one. So we have a local function f of phi, which is the usual quartic form with, in the case of phase separation, negative a. So I have the curve on the right here for essentially the bulk free energy density. I construct a square gradient free energy, this curly f, which is in the middle there with a kappa grad phi squared over 2. The chemical potential is the functional derivative of that. So the chemical potential is telling stuff which way to move. And in the case where you have negative A, so that you have 2 minima in the free energy, then I'm just reminding you that the phase equilibrium that you'll find, the steady state of the system in an equilibrium model like this is found by the common tangent construction. In this case, with the symmetric free energy, I just connect the 2 minima of the free energy. And if the composition variable, the density, lies between those two, it will phase split into the 2 minima via the common tangent construction. So in that construction, the chemical potentials are equal in the two phases. And the second thing you need to remember is that the pressures are equal, where in a thermodynamic equilibrium system, the pressure is mu times phi minus F. So that's the passive case. And the simplest way of adapting that to an active system, so you have to do something, otherwise you obviously won't get anything new. The minimal route to breaking detailed balance, breaking time reversal symmetry in this setting is to add to the chemical potential this term in red here with the coefficient lambda. This is called active model B. And we've been looking at it for a number of years now. So the important thing is that lambda grad phi squared piece in the chemical potential is nobody's functional derivative. So this is a minimal way of breaking time reversal in these systems, and it does so by breaking the free energy structure. But this model keeps the idea that the current is the gradient of a chemical potential. And you can see something is already missing there in this very minimal model, which is that current, on average, cannot have a curl. And so the kind of thing I was showing you with this cog rotating in a bath of bacteria, it's going to be very difficult to get that kind of physics out of this kind of model, because there you want there to be a continuous large-scale circulating current. So you want the steady state current to have a curl. Nonetheless, this is the minimal violation, and it is one which you can not derive, but specifically motivate from microscopic considerations of active Brownian particles. So the effect of that on motility-induced phase separation is to change the equilibrium conditions. If I define a chemical potential as the lambda term doesn't change the bulk chemical potential because it's a gradient term. So I can still equate the bulk chemical potentials, and they are equal. The thing which thermodynamically would be the pressure is not. And this is something we call the uncommon tangent construction. So if you look at the drawing on the right, you have an offset in the common tangent construction, which looks like a pressure difference between coexisting phases, and that is a function of lambda, which we know how to calculate. So the way in which you find coexistence in this kind of non-equilibrium model is you assume an interfacial profile in one dimension, so some tangent-like profile, although that won't exactly be what the function is. You say that there's no steady current from left to right across this interface, and with fixed boundary conditions far away, that's appropriate. So that's very easy to see why the chemical potential-like quantity is equal. And you seek a solution of that with no gradient at infinity. And you find, because of this lambda term, the normal equilibrium conditions do not apply. So we call that anomalous phase separation, or anomalous phase coexistence. And I'm cheating slightly with this slide, but it is definitely a thing. It is something which is repeatedly found in active phase separation, that you cannot rely on anything like the Maxwell construction or the common tangent construction to find your phase boundaries. And there are several models in which this has been established, some of which are analyzed the way I've said, some of which are a bit different. But anomalous phase separation is definitely a success of this particular continuum model, active model B. But it's not really enough, because there's no cluster phases, and as I said before, there's also no circulating currents. So something is missing here, and the mathematics of it is a little bit tricky because it's not missing in one dimension. What you find is that if you do a Taylor expansion in gradients and fields, and you ask, well, what's the general form that I'm allowed at this order in a gradient expansion? You pick up this term I've shown here with zeta, and what I'm saying is that there are actually two terms. Well, there are three things you can write down at this order, which could live in the current equation or modulo one more grad in the chemical potential equation. Two of them are linearly independent. And by choosing the coefficients to be zeta of the thing I've shown there and lambda of the original grad phi squared, the thing in square brackets in the J equation there vanishes in one dimension. So that's a convenient thing, because it allows you to think about the role of zeta in a much more precise and targeted way, because you can keep reminding yourself that it vanishes in one dimension. And that means it also vanishes for a flat interface, because if I have an interfacial profile phi, which is a function of a single variable, that term vanishes. So already you can see that that term has something that kicks in when I have curved interfaces around, and this will turn out to be the key point. So I have these two terms which separately break time reversal symmetry. They break detailed balance, one by destroying the free energy, one by even destroying the idea that J is somebody's gradient. As I've said, that term that vanishes for a flat interface. Now, what that means, because it vanishes for a profile that depends only on one coordinate flat interface, if I calculate bulk coexistence at the level of mean field theory, this term will not come in. So it appears to have no effect on bulk coexistence, but because it comes in when I have droplets, it can actually stabilize phases of microphase separation, as long as they have curved interfaces. So let's go back. This is the active Brownian particle simulations again. This has been put on a density scale. Now you can see in the liquid phase here, the yellow phase, there are these droplets, these voids. And these persist even when this coarsens indefinitely into a steady state. So if you look at the life cycle of those droplets, they form in the middle of a piece of liquid and they pop out at the interface. And the first important achievement of the model I've just described with the zeta term, active model B+, someone's annotating my screen again, is this. So if the person who put the orange line on my screen, thank you. Anyway, so this is a steady state phase separation. There's one droplet crossing the periodic boundary conditions. Liquid droplet, it has vapor bubbles in it, and you see they have a life cycle. The little bubbles are formed in the middle of the droplet, they migrate to the interface, and then they pop out. That's a manifest breaking of time reversal symmetry, just as striking as the rotating cog. And you see it in active model B+, in this case for positive zeta. So there it is again. What's next? Yeah. So I want to say a bit more about how to analyze this current. So that zeta term I'm now writing as J sub zeta. And what can we say about it? Well, firstly, any vector field J sub zeta can be written as the gradient of something plus the curl of something else. And what we're interested in the context of phase separation, although I emphasized currents before, is we're actually interested in the dynamics of the density. So the curly part of this current is invisible for phi, because in phi I take the divergence of the current. So phi dot couldn't care less about the thing called H here. So it has interesting properties, but for the purposes of looking at phase coexistence, we can forget it. But then, and this is of course the standard Helmholtz decomposition of a vector J, then I'm left with I can still think of the whole problem in terms of a chemical potential. J becomes the gradient of a chemical potential, but it's non-local. And it looks like a Coulomb integral. So I've written that down in 3D here. So this is just the standard construction of how you decompose a vector field via its divergence and curl. So what that looks like is a Coulomb integral, if I think in terms of electrostatics, where the integrand has a dipole density. And because I said that J vanishes for a flat interface, it shouldn't surprise you that the thing which enters here is in the div J is something which is proportional to curvature, or at least a power of curvature. So in the neighborhood of an interface, I pick up a non-local contribution to the chemical potential which cares about curvature. So that's summarized what I've said already. The zeta term fundamentally changes the way curvature influences what is effectively the chemical potential for this coexistence problem, and it allows microphase separations to arise. And depending on the sign of zeta, these can be bubble phases or cluster phases. The ones you've seen so far have been bubble phases. So here's a bubble phase. So just to emphasize that we can also talk about cluster phases this way, there's a symmetry of the whole model that I wrote down, which if I change the sign of the composition variable and both of the activity parameters, zeta and lambda, the whole theory is mapped onto itself. So what that means is if I only change the sign of zeta, then, and lambda as well, if I want, is I map phi onto minus phi. So just graphically here, magically, by changing the scale on this plot, I've just reversed the scale. This is now cluster phase. So the theory can talk about bubble phases, it can talk about cluster phases being the one more pertinent to the experimental observations, the bubble phases being more pertinent to the numerical observations on active Brownian particles. So this is what the dynamics looks like. You see that in the bubble phase, things are happening. They're not just sitting there as a kind of static microphase separation. Bubbles have their own life cycle, even in the absence of the boundary of the fluid phase where we saw them popping out before. So I'll come back to this in a little while as to what we can say about this life cycle in the stationary state. So here's a phase diagram. I've drawn it for positive zeta, where you get the bubble phases, but you can just flip it over, the same trick as before for negative zeta. So for modest values of the B plus activity parameter zeta, I get a standard sequence of vapor liquid phase coexistence, the two pictures in the middle, and then liquid. And if you do that for a large value of the second activity parameter zeta, then you find that the liquid phase has the bubbles in it. So it's actually that second picture on the bottom is a coexistence of a bubble phase or microphase separated state with excess vapor. And then as you increase the density, a uniform bubble phase, and then finally a liquid. So how do we understand this? So we can talk about bubbles, we can talk about clusters, but within the frame of this continuum theory, with its active terms, what's going on to stabilize the microphase separation. So let's do that for droplets. And again, the best starting point is to remind you with what happens in the passive case and then say how that has to be changed to deal with the active terms in model B+. So I remind you that if I have a passive system, so here I've got a liquid droplet in a different coloring convention, but in this drawing, a liquid droplet coexisting with its vapor. And in the near the surface of a liquid droplet, the chemical potential is raised by a term shown in the top line here, which involves the surface tension, the binodal density, and the radius of the droplet. And this is simply because the Laplace pressure inside that droplet is positive, so particles have a preference to leave and go to somewhere which has a smaller Laplace pressure and therefore a bigger droplet. But if you only have one droplet, you can calculate the current onto the surface of the droplet, which controls the rate of change of its size via the gradient of a chemical potential evaluated at the droplet surface. And there's an expression given here, which involves the ambient far field chemical potential mu infinity rather, mu I, which is this specific equilibrium value of the chemical potential at a curved interface, and 2 powers of the radius, which come from solving the diffusion equation and the Laplace equation for mu. So a single droplet coexists with a vapor at a displaced chemical potential, in other words, a vapor with a supersaturation. And as I'm sure many of you don't need reminding, if you have many droplets, the ambient supersaturation is set by the mean droplet size. And what that means is that droplets which are bigger than the mean droplet size have a positive growth rate, and droplets which are smaller than the mean have a negative growth rate. And that's shown in this equation for R dot, the rate of change of size of any given droplet in terms of mean size R star, which is a function of time, and the instantaneous droplet size itself. So if you draw a graph of R dot against R, you get this famous result here. And this, as I just mentioned, this is R dot of R. It has a fixed point at R star. Any droplet that is bigger than R star will grow. Any droplet that is smaller will shrink. Because of that, R star itself will grow in time, and it's possible to work out all the details of this. So this is beautifully reviewed in Alan Bray's series of papers and his review articles. So large droplets grow, small ones shrink, extremely unfair, but by that process, phase separation always goes to completion. If I have a system where large droplets grow and small ones shrink, then the only ultimate a stable stationary state for that has one massive droplet coexisting with its vapor, or in an infinite system, a flat interface between the two phases. So the other important point, which is emphasized by Bray, is that this process he is described by what he calls a zero temperature fixed point. If I look at the picture at the bottom right here, I don't need to worry about noise. There's noise in the initial condition, it's got some randomness. That can be evolved deterministically and will just take me downhill right the way to the phase separated state. So noise is important for nucleation, but once you have droplets in play, noise can be ignored. Right. So how then does the active contributions to the continuum model alter this scenario? Well, what I said was that in the active system, there are two distinguishable contributions to the chemical potential everywhere. I'm interested in the chemical potential just outside a droplet because that's what determines the flux. In other words, if I know the chemical potential just outside the droplet, then I can solve a quasi-static diffusion problem with the droplet boundary as a sort of boundary condition. And from that, I can work out the flux onto the droplet. That only depends on the chemical potential just outside, because that sets the amplitude of a decaying diffusive density field. So I've said that there's this non-local contribution, which is proportional to zeta. And I've written down again there. It looks intimidating. But if you look at that object, it's got lots and lots of gradients in it. It's only large near an interface because in any bulk region, the gradients will be small. So I get this thing which looks like it looks like an electrostatics problem. The chemical potential contribution looks like the Coulomb the Coulomb potential for a dipole layer pointing across that interface. So the details of that don't particularly matter, except that importantly, it means that this contribution is also 1 over r, so the same scaling as the first term from the interfacial tension, and it's proportional to zeta. And zeta, as I've said, can have either sign. So if I go back to the top equation, I've got 2 contributions to mu for the chemical potential just outside the droplet. There's a passive piece and there's a zeta piece. And zeta can be anything. It can be as negative as I like. So the sign of the effective interfacial tension for the Ostwald problem is something which can now be negative. So if I choose zeta with the correct sign and make it big, it will always outweigh the gamma term in the top equation. And therefore, I expect a regime in which the Ostwald process is reversed at high activity and only if I choose the right sign. The sign to choose will be different depending on whether I want this to happen for droplets or for clusters. So that's the normal Ostwald diagram, and it becomes this. So this looks like Ostwald ripening with a negative interfacial tension. But I have to emphasize that it's only for the purposes of Ostwald ripening that the interfacial tension appears to be negative. If I come along to one of these droplets and I perturb the interface, it will not be unstable. The spherical droplet has a stable, or circular droplet has a stable interface, but for the purposes of calculating the mean flux onto it, I can put a negative value of the interfacial tension into the Ostwald equation and I will get the right answer. So, yes.
I have a quick question.
Yes.
So is the 1 zeta over r correction to the chemical potential, is that true in all dimensions or is it only in 3?
That's an excellent question. It's certainly true in 2.
Okay.
All, I would hesitate, but I think so. Yeah, I think that structure is because yeah, obviously it doesn't happen in 1 anyway. So the ones that matter are 2 and 3, and it works in both of those. Although obviously the actual expression I gave for the Coulomb integral would be different.
Yes. Okay. Thank you.
Okay. So what that means then is, if I have reverse Ostwald ripening, that's the socialist version of Ostwald ripening. Small droplets grow, large ones shrink, so they all end up the same size. However I begin, noise doesn't matter. If noise didn't matter, as in the equilibrium case, any initial distribution of sizes converges to a delta function at some characteristic r star. With noise, actually, life is more complicated because in the presence of noise, the size that you end up with does not depend on the initial distribution. It forgets the initial distribution because of the noise. And that's because of what we saw, what happens here in the cluster or bubble phase is you have this dynamic process. So there isn't a sort of conserved number of droplets. And the physics of how this chooses its size is interesting. And it involves a competition of a number of effects, which we have looked at numerically, but there's not really any theory of this, which is written down here. So the noise will allow new droplets to form by nucleation. Droplets can evaporate, but they mostly disappear by coalescence. We saw a little bit of that in that movie. But all the time that's happening, the reverse Ostwald process is trying to make them all the same size. So it pulls the size distribution towards uniformity. So there's a balance of these birth and death and pulling together in size that is responsible for the mean cluster size r star as it depends on the parameters of the model. But the other thing to say is that in the steady state in that movie, there's a life cycle. droplets form in one way, they disappear in another. Form by nucleation, disappear by coalescence. Doesn't look the same if you run it backwards. Because if you run it backwards, you find that they were formed by splitting, and that's not what happens. So the steady state life cycle, in which again, in active model B+, you are seeing this manifest breakdown of time reversal. So what I want to do next is change the topic a little bit and talk more about.
Mike?
Yes, please.
Can I ask a question about this before?
Yes, go ahead.
Going back to the particle picture, the
Yes.
picture of active particles moving along, can you explain maybe what is the qualitative difference in that picture, moving from a positive zeta to a negative zeta? Sorry.
I don't know if I can actually, because what we haven't been able to do is to kind of unlike the lambda term, which we can pretty much connect to microphysics by explicit coarse graining. If you want to coarse grain yourself from a microscopic model all the way to the zeta term, it's not very easy, and we haven't done that. I can't identify the specific physics, except that what I can say is it appears in active Brownian particles, I have one sign of zeta, and it appears that in experiments with the surfing autophoretic colloids, I have the other sign, because the experiments show me cluster phases and no bubbles in the liquid, and in the ABP simulations, it's the reverse.
Yeah.
So there's an interesting line to pursue there, but we haven't taken it to the point where we can say, here's a mechanism for that.
I see. I'm just looking for something that will create mean reversion, like you describe it here, in terms of the size of the droplets that are forming, just from a microscopic.
No, that's a good question. Okay, yeah. So one should be able to. Okay, so that's a good question, which I don't have an answer to because we haven't actually thought about it in those terms. You should be able to think about basically the kinetics of particles leaving and arriving at the surface of a droplet and explain why the Ostwald process has gone into reverse. So that's a very interesting suggestion.
Mike?
Yes.
Well, let me make I'm not sure it's a comment or a question, but it's related to this point. I mean, okay, you have a field theory for one variable. This is your phi, which is presumably the density field of the colloids in this colloid problem.
Yes.
Now, in the colloid problem, actually, we have the colloids and we have the substrate, etc., or product and end product. So, in fact, there are two fields there.
Sorry, what was the second one? What was the second one again?
The substrate, which means, normally what happens is that there is some catalytic reaction.
Oh, yes. No, I understand.
Right.
Yes.
So there are, in fact, at least two fields in the colloid game. And once you do this, and we played this game with Shura Grossberg, actually, then it turns out you can get these clusters sort of directly, and you can get essentially a physical argument for the sign and everything.
Okay, so that's a very useful comment. So I think, So the idea of having the single variable. So there's only one conserved density. Well, no, in the presence of the chemical reactions, there are other conserved densities. But I mean, obviously, we were aiming here at minimalism. Right. And it's true that you can decorate this kind of theory, certainly with explicit, and we've done a bit of that. Where I had a postdoc called Benno Liebchen, who's also done these kind of simulations with explicit concentration fields for reagents and products and so on. And indeed, you can get microphase separation that way. I think, but it's not the only way to do it. In other words, the microscopic physics underlying the microphase separation, in my opinion, is probably not very universal. There are probably a dozen different mechanisms you could put together that would do that. And a question is whether there's some convergence among those theories to at least an underlying structure, particularly if, as in a minute, we start talking about critical behavior, that is more universal.
Yeah.
So in a sense, we've sort of deliberately steered away from digging into the mechanism by adding more detail, but I'm sure it can be done. So thank you for both of those questions.
May I ask a question?
Okay.
So the active model B plus, does it contain all the terms that are relevant as we are looking at larger and larger scale?
That's my next topic. So
okay.
Let me talk about that in the next.
And if I may, so when you have a look at the equation of motion, can you see whether the specific terms are breaking time universal symmetry by just looking at it, or should we compare it to all the terms that can be possibly driven from the free energy?
Well, yeah. So this is again sort of coming up in a bit.
Okay.
They do explicitly break time reversal symmetry, and the proof of that is en passant in what I'm about to say.
Okay.
Mike, before you go on to entropy production, I have a quick clarification. If you have a model of, say, active Brownian particles with just quorum sensing,
yes,
is the zeta term present?
Well, I mean, okay, no, but if you have active Brownian particles with quorum sensing and an ordinary thermodynamic repulsion of finite range, then yes. So I mean, we did explore this a little bit more than I've said. So if you have both a V of rho, a quorum sensing type interaction, and some sort of enthalpic repulsion, then you expect both of these terms. If you only have V of rho, you can only find the lambda term easily.
Okay, yes, thank you.
But generally, of course, in any, if you only find one of two possible terms in a Landau expansion, though, it suggests your model is rather incomplete, rather than that the Landau expansion is too complete, if you see what I mean.
Of course, yeah.
Unless you've missed a symmetry, which of course time reversal is one. Okay, so let me address this issue of time reversal in steady states. So brief reminder: arrow of time. ds by dt, rate of change of entropy of the universe, is positive. That's the arrow of time. Once you reach thermal equilibrium, the entropy of a closed system ceases to increase. And the corollary of that, as I've mentioned several times already, in a thermal equilibrium system, barring magnetism, you cannot tell if a movie is running forwards or backwards. So you have an arrow of overwhelming probability, which is the second law of thermodynamics, which lands on a time reversal symmetric stationary state. And of course, that second statement is not true in active systems. So, and here's an example. This is a stationary state. It's got a bubble wrapped around the periodic boundary conditions I showed you before. And the fact that these voids leave the surface of the macroscopic liquid droplets and don't enter it is manifestly not time reversal symmetric. And just for avoidance of doubt, that is the time reversed movie. And you can tell the difference. So the question is how to quantify this. Well, this brings us to the topic of stochastic thermodynamics. The entropy production can be in what is the very important but kind of somewhat unacclaimed generalization of the second law, given how important the second law is, achieved by a number of people in the past 2 or 3 decades, is that you can relate directly, even at a microscopic level, the entropy production to the ratio of probabilities of seeing a forward and backward movie. So the arrow of time is telling you that a forward movie towards equilibrium is infinitely more likely or thermodynamically more likely than the reverse, but this is a much more general idea. So if you can observe, measure, or in a field theory calculate the steady state entropy production, it is telling you how irreversible that steady state actually is. And some important points. That quantity, the probability of seeing a forward sequence and a backward sequence, depends on the scale of observation. In other words, if I do some coarse graining and I throw away information, I change those probabilities because they get lumped together in different ways. Field theories intrinsically are coarse grained, so any entropy production we calculate from a field theory is not an attempt to completely capture all the microscopic irreversibility in a model. It is an attempt to quantify the visible irreversibility at the scale of measuring continuous fields and things that we want to work with. And we may want to coarse grain further. I'll say about that in a second. And the other thing is that the entropy production is directly calculable from the path integral for the field theory. So very briefly on that last point, I don't want to labor this, but we have an equation of motion. Phi dot is minus div j. There's a sign missing somewhere. There's a formal way of constructing the probability of a phi of t, so a time-dependent field configuration. And I can construct that for the forward and the backward dynamics. They involve the chemical potential from which I've separated now into an equilibrium and non-equilibrium part. So the non-equilibrium part, which in the Zeta model includes the non-local piece. If I look at the equilibrium part, and this answers one of the questions, this thing that appears here is a total derivative of the free energy functional, which is the same as saying that the steady state entropy production is 0. But there's a piece which involves the non-equilibrium part of the free energy, which gives me a steady state entropy production, which is given by the bottom line of this slide. It involves an average of the rate of change of the field and the non-equilibrium part of the chemical potential. So you can think of this as a rate of work which is being done against the density field by the microscopic dynamics. And there's a factor of d, which is the noise variance. So as you can see from that last equation, actually, we could have long arguments about this, but at least mathematically it's possible to write the entropy production as the integral of a local quantity. So I can define an operator, sigma, whose average is the entropy production. And this operator, for the case of active model B, I'm not talking about the zeta terms in these next few slides, looks like that. I know what phi dot is, and statistically I can write that purely in terms of phi and its derivatives, which is very intriguing to me because it says that I can calculate the global entropy production directly from the stationary measure. If I know the probability density of different states, I don't have to know what order they appear in. I can calculate the entropy production. Of course, it matters what order they appear in because the movie is either symmetric forward or backwards, or it isn't. But I do know the dynamics in this model. So given those dynamics, if you tell me the stationary measure, which is something I can easily get from simulation, I tell you the entropy production. And you can see what's living in here. It's got polynomial bits, gradient bits, but this is something which has structure. And in particular, what we find is that wherever there's an interface, so wherever I have a situation like the one on in the drawing there or on the right, there's a big peak in the entropy production at the interface, and that peak does not vanish in the limit where I turn the noise down to 0. So in the deterministic dynamical limit, there is still an entropy production at interfaces in these systems. On top of that, there's a much smaller entropy production in the bulk, which does vanish as I turn down the noise. So what that's saying is that if I look in a piece of bulk, I have to study the time movie of the fluctuations before I can tell whether the system is running forwards and backwards. If I have the stationary interface there's something happening at that interface, which is a bit like the rotating cog. It's giving me a constant, non-fluctuating contribution to the entropy production. Okay, so that's handy. But then the other thing that I want to address and perhaps finish on this, I think I'll leave out the hydrodynamics part, is this question about how, if I now coarse grain further, how does the entropy production behave? And the context in which one is likely to want to coarse grain further is when you examine critical behavior. So I've not talked about the critical point of MIPS, but it's a liquid vapor phase separation. It has a critical point. There will be some density and some level of activity at which the system just begins to phase separate into two nearly identical phases. And then the question is, near that critical point, can we say anything interesting about the entropy production and its scaling? And the idea is that you might find, for instance, that if I, at a high resolution, I'll see mesoscopic or microscopic motion that is clearly irreversible. And if I zoom out from there at low resolution, I might pull back to a situation where the dynamics looks reversible. So I'm going to skip the next slide, but if you want me to show you that movie at the end, I will do so for fun. So what might one expect for the renormalization group flow, so the scaling as I zoom out of the entropy production in near a critical point. So there are various scenarios. Suppose I have a system without with unbroken time reversal symmetry, for instance, model B, and then I break it with some activity. Then there is a natural scaling of entropy production, because we know that it's, well, if I think of well, it's a dimensional argument basically, so I shouldn't elaborate in detail, but there's a scaling which is that I've got something happening per unit volume, per unit time. There's a natural scaling in terms of the correlation length, which says that, say I have a spin model, so some coarse-grained Ising model, a piece the size of the correlation length flips over once per correlation time, and each time there's a kind of flip like that, something irreversible happens. So that's a way of understanding that scaling, but there are many other ways to derive it. So there's a natural scaling. So this plot shows what might happen in those natural units to the entropy production. And one thing which can certainly happen, okay, so you coarse grain, you've got these active terms, you move away from the initial place, and you could end up in some manifestly active model. So what I plotted vertically is other features like critical exponents for the model. So the way that the model behaves, the way its correlation length diverges, etc. So that's perfectly possible. The other thing which you might expect is something like this, where the activity is irrelevant in some colloquial sense, not quite in a technical sense, and I flow back to a model which is different from the first model, or it could be identical, it could come all the way back to 1, but has no entropy production. In other words, that when I zoom out, I see an equilibrium model. That's a perfectly conceivable outcome. And a good question is what happens for MIPS, which is this augmented model B. So there's a calculation you can do explicitly. This is only for the lambda term I'm talking about now for simplicity. It's irrelevant. In the formal renormalization group sense, it's irrelevant. It doesn't change any of the exponents of the model the way one would normally think about. But there's a little surprise coming, so it's not quite as irrelevant as it looks. Still, I can work it out. If I've got this operator which is telling me the entropy production density, I can see how it scales. The finite part of it scales order 1 in the natural units. So it's irrelevant in the sense that it doesn't change what is above 4 dimensions, the Gaussian fixed point, but it doesn't go to 0 either. So entropy is production is order 1 per space-time correlation volume. So that's interesting. And that is the active model B in D bigger than 4. So this is what I had before, and what that I've just described actually corresponds to is this. Namely, I have a model whose other features, other than the entropy production, it goes to what looks like an equilibrium model. It's irrelevant. I mean, and I meant it in the formal RG sense. The additional active term is irrelevant. This model is in the same universality class as model B. But this model has an order 1 entropy production in active units, in natural units. What does that tell you? That actually tells you that model B also has order 1 entropy production in natural units, except that its coefficient is 0 because it's got time reversal symmetry. So within the class of model Bs, there are reversible versions and there are irreversible versions. They're in the same universality class. They have a scaling above 4 dimensions of the entropy production, which is the natural one, not going to 0. But of course, if there's no entropy production in the original equations of motion, I can coarse grain as much as I like and I won't generate the lambda term because it's irrelevant. So that's the way we understand this now, which is a little different from what I was expecting. We call that stealth entropy or stealth time reversal symmetry breaking. So I have a model which is in the same universality class as an equilibrium model, but breaks time reversal symmetry at order 1 in natural units. So what about between 2 and 4 dimensions? So this then becomes a bit hair-raising, and you can read the details in this paper we published last year. There's a technical obstacle. Sigma the entropy production density locally is an irrelevant operator in the field theory. And what you find, and by far the best source on this, is the wonderful, still wonderful book by Danny Amit on phase transitions and critical phenomena. You find that the RG flow couples all irrelevant operators of the same order. So to calculate what one of them does, you have to calculate all of them. And in active model B, even with just the lambda term, forget zeta, there are 20. So you have to do a 20 by 20 kind of matrix renormalization group, and this exceeds the lifetime of a PhD thesis in the UK. So we didn't. But Fernando Caballero, the excellent student who did this work, we did do it for active model A. So basically, you just forget about the conservation law. You've got another model which is still active because the lambda term in the chemical potential still breaks time reversal. It's not directly connectable to the MIPS that I was talking about before because it's not got a conserved field, but it still enables you to address this question of principle. So that reduces this to a 7 by 7 problem, which only takes about a year. And that was the rather painful final year of Fernando's PhD. And the result is quite interesting. So above 4 dimensions, you have exactly the same scenario as in B. So the active model A is a type of kineticizing model. Above 4 dimensions, I have the non-trivial entropy production set by the natural units. And of course, in the case where I turn off lambda and I get a reversible kineticizing model, it has 0 coefficient, but it's still there. In less than 4 dimensions, there's a new critical exponent, which in the epsilon expansion comes out with a positive exponent. So the reduced entropy production actually diverges at criticality, even though this model has the same formal property that the activity is irrelevant in the ordinary renormalization group language. So this is quite interesting. I'm not quite sure entirely what it means yet. But anyway, we know that. So this is just a reiteration of what I said before in relation to model B. I have a model, and this now we know even below 4 dimensions, is in a universality class which contains both active and passive members. In that sense, it looks like a passive model, but it has non-trivial scaling of the entropy production. Of course, there isn't any entropy production in members of that class which are reversible, but that's because the amplitude vanishes, not because there isn't a scaling. And we certainly expect the same outcome now in active B and B plus below 4 dimensions. So that would be a good place to stop. And sorry to overrun a little bit on the time, but thank you for your attention. And that was just my agenda. And I'd welcome any further questions if there's time for that. And I'm happy to stay on if many people want to leave and some want to remain.
Thank you very much for the talk. Any questions? We're open for questions, so feel free to jump in.
Can I ask a question?
Sure.
So I want to ask about the reverse Ostwald process. So you've mentioned that it has to do with the chemical potential being rising from a dipole density on the boundary of the bubbles. And so if I think of 2 spherically symmetric bubbles, it seems that by symmetry there should not be coalescence. So do you think that it's something that coalescence has to do with fluctuations, or should it appear already at mean field level?
So good question. Coalescence is not part of the Ostwald process. The Ostwald process is shrinkage of one droplet and expansion of another. So coalescence actually requires diffusion of the droplets. So that does require noise. Yeah, so once if you've got a phase separation, once droplets are disconnected, and I mean I talked about the 0 temperature fixed point, that is the pure Ostwald process, but the coalescence droplets only happens when they start moving around, which is diffusive and noise driven.
Thank you.
Hey, Itzhak, you have a question?
Yeah, like, okay, but I was trying to think about a simple explanation for this irrelevant operator stuff associated with the non-equilibrium contributions. So isn't it simply the fact that these non-equilibrium contributions are associated with gradients, sort of high gradients, and that's why they're associated with interfaces? And so basically, I mean, you know, when you look at bulk terms, which is presumably what is behind these relevant operators, is that there is no difference, and the whole difference comes from the interfaces.
Yeah, I don't disagree. I mean, the reason that they're irrelevant is because they are higher order. They give me very high derivatives in the equations of motion. So it's very easy to to see why they're irrelevant. So, but I mean, the naive thing would be saying,
just lower dimensionality, basically.
Yes. So, but then, as I was mentioning, if you read in Amit's book, I mean, there's this whole theory about the scaling of irrelevant operators, and a lot of them have non-trivial behavior. So normally you're not interested in them because they don't change the universality class that you're in, but that doesn't mean you can't ask how they behave.
Right.
And in this case, then you have to, as I say, you have to interrogate them to get the answer to the particular question I was addressing.
Right, but I mean, normally when we talk about thermodynamics and all this analysis normally involves thermodynamic limits, so we are not interested in surface terms. While in your case, the game comes from the surface terms.
Yes, I mean, I agree, except that, of course, if you really are close to a critical point, it's a bit dangerous to talk of the gradient terms as surface terms because there are fluctuations everywhere and gradients everywhere. So,
okay.
Yeah.
Okay, that's true. Okay, thanks.
Thank you.
Any further questions?
Yeah, I have a question. Hi, Mike. How you doing?
Hi.
So, I was thinking, what the ability of these theories of predicting certain global effects that we observe in active systems. So, for instance, if you introduce some objects like wedges in the middle of the box, we know from the experiments by Austin and Chagin that the mass will move to one side of the box. So, I wanted to ask you about what the relevant boundary conditions would be for one of these theories if you were to if you wanted to introduce one of these objects in the field, and how you would capture these global effects.
So that's that's a good question. So okay, so the one comment is that obviously, and I didn't have time to talk about the model H in hydrodynamics. I mean, you don't have a conserved momentum, so you have to be a little bit careful when you're talking about the mechanical interaction between the active particles and say an object. But we are working on that, particularly Patrick Piazzonka in my group is looking at that now. And of course, you can, within this kind of model, you could, for instance, have a system with periodic boundary conditions, and you can put in, for example, a triangular-shaped region where there's an external field which basically says the particles shouldn't go there. So you can do that with a kind of conservative external perturbation, which mimics the idea of an obstacle. And then you can ask, is there now a circulating current around the periodic boundary conditions caused by essentially putting a ratchet-like object into that system? Okay. And we don't have a complete answer to that yet. It turns out to be a bit harder to make that happen in this model than you might at first think, but it can be done. But that's something we're still working on. Connecting that closely to an experimental geometry, I think, is going to be difficult. But to establish in principle the idea of a sort of geometric ratchet at the level of this type of theory, I think should be possible.
Okay, so you introduce some kind of perturbation to the field rather than...
Well, you put in something like a localized external field,
right? So
which basically says the equilibrium value of phi here is different from the normal one. And then that should be enough to give you gradients elsewhere, which will maybe drive macroscopic currents.
Okay, all right. Thank you.
Okay.
Can I ask, Mike?
Please.
So actually, I'm outside this topic, but when you started with equations, and I remember you added to the flux noise, and this, I assume, comes from the microscopic physics that you omitted. But the bottom line of this talk, there is time reversal symmetry, but that noise is still a time reversal correlation function.
Excellent question.
So
another way to break the time reversal symmetry in model B is to violate the FDT. for instance, to have a time local mobility, which since it's one, it already is, but put in colored noise, for example. And that is a different theory, and it's not the one that is suggested when you do the coarse graining of the microscopics. And I think other people, or I know other people have studied that type of theory. And it's an interesting question as to, well, maybe you should have that as well. But in the active model B system, if you do coarse grain it, obviously if you coarse grain active model B, you don't get, sorry, if you take active Brownian particles and you coarse grain it, you don't get straight to active model B. You get to something with a rho log rho, etc. But you do get to something which looks like an ordinary free energy, an ordinary noise, plus a term that breaks the free energy structure through the chemical potential. So the original inspiration for active model B was from coarse graining the active Brownian particles. And it's true that if you just sat down with a blank piece of paper and said, what's the simplest way to break time reversal here, you might have come up with what we said, or you might have said, well, let's just break the FDT on the noise. But one of the interesting things, of course, is that we are finding things like an entropy production which is non-zero in the zero noise limit, which I don't think I think that kind of physics would not emerge if all you'd done was to break the relation between the noise and the dissipation. But if you go to the particle level, it's in fact moot, because there's this model of active Ornstein-Uhlenbeck particles, which behave almost exactly like ABPs. And all you do with those particles at particle level is to break the FDT between the damping and the noise. You put in colored noise and instantaneous damping. So there is actually probably a connection between these two different ways of breaking time reversal that we haven't in detail understood yet.
Thanks.
Yeah, other questions?
Maybe one more.
Yeah.
So when you had to look at the entropy production, basically entropy production was written in the form of the Kullback-Leibler divergence.
Yes.
Yeah, and that quantity will be, you will be able to add this quantity over the space if each point on the space of the space are independent with each other, although there is a correlation length in the dynamics we are looking at. So how can you justify this local feature of the entropy production?
Well, so this slide is calculates the forward and backward path properties for the whole space-time configuration of the system. And when I take the ratio in the middle there, I get the integral of something as my entropy production, and the bottom line, there it is. So the point is that that object, all I can say is that the global entropy production is the integral of a local quantity. That is actually slightly different from saying that I am confidently defining a local entropy production, because there may be more than one way. I mean, I can integrate this by parts. I can do all kinds of things. I can do things which move contributions to that integral from one place to another, whilst maintaining the integrated value. So I think this part maybe partly answers your question. The fundamental thing is the global entropy production, but the fact that it can be written as the integral of a local quantity makes it interesting to understand the scaling of that local quantity. Because if I do a coarse-grained, the idea of the RG, if I do the coarse graining of the model, is I will generate configurations at this coarse-grained scale with the detail missing. And so if I know how that thing on the right-hand side of that blue equation at the bottom behaves under RG flow, then I do also know what happens on the left, because one is just the spatial integral of the other.
Okay, thanks.
But there's a tricky technical point buried there. We know at least 3 different ways of writing the right-hand side, just basically to do with integrating different things by parts. And if you then start plotting those functions, say across an interface, you do get different looking results. So the interpretation of this as directly as a local entropy production is not unique. And just to put that a different way, if I have an entropy current, which is moving entropy from one place to another, then anything which involves the divergence of that current looks like a local entropy production because the entropy is going up and down, but when you do the integral, will disappear. So the definition of a local entropy production is more of a mathematical formality at the moment than something which you are really entitled to attach physics directly to.
Matan?
Yes. So I have a small question about something you haven't really focused on, and I wonder if you've seen or looked a little bit in your simulations, and it's the dynamics and more specifically the flow correlations inside the dense phases. Because for example, you can get, I think, for free, you can get vortices. Do you see that? You focus mostly on the densities. Less on the velocities.
Yes, I did because I'm just phase around. So yes, so a good question then is if we say in that
specifically since vortices can give you, if they have a typical size, they can give you curvature, and curvature plays a really important role here in many places. So I wonder if.
Well, okay, so let's just look at this movie again because it obviously. That's the time reversed one. Sorry, trying to go back. Yeah, so there's curvature in at least two different scales here. So I think what you're saying, which is a good question, is if I plotted a map of the current, J, here, would I see interesting structure in the current? And that's a good question. I don't have a proper answer to it. The statistics of that from the simulations can be slightly problematical, but really we should have done that by now. And I don't have an answer, but should. Yeah. So the question is, for instance, in this system here, on what scale do you see patterns in the current? And I don't have an answer to that at the moment.
Thank you.
Suraj?
Hi, Mike. I have another question about entropy production. So So you showed that there's this stealth entropy production, which in natural units has a non-trivial scaling below 4 dimensions.
Yeah.
And now if you use, so if you go back and think about, the things you'll have already done, which is regarding connecting entropy production to fluctuation dissipation violations via Harada-Sasar, then can you, is there something you can say about how this new exponent might affect the usual scaling identities that you get so in equilibrium, when you get Fisher's identity that relates the susceptibility exponent to the correlation anomalous exponents? Does that change, or would it change when you include?
I think any scaling. Someone needs to turn off their mic. Any scaling that can be identified in equilibrium should be maintained, at least near the critical point, because of what I said about the activity being irrelevant. So if I look at correlation functions and things, and any exponent that describes the behavior of an equilibrium, or a correlation function that is defined for the equilibrium should be the same, I think. So it's only when you'd have to construct a correlator which was specifically testing whether the forward and backward correlations were the same. So, and I think you could do that, but it wouldn't be one whose scaling is already known. It'd be something like phi r0, phi rt minus phi r0, phi r minus t, something like this.
I see. So maybe the way one should understand it is that because although you have although fluctuations and although you don't have the fluctuation dissipation theorem applicable even in the continuum limit, because their difference integrated is related to the entropy production rate. That difference is scales in a different way and doesn't change the scaling identities in this context because activity is irrelevant, but there might be other contexts where scaling relations can change.
Yes.
Okay.
I think.
Okay, any other questions? Okay, so thanks again for the beautiful talk and your time. And
thank you very much for listening to me.
Bye, Mike.
Goodbye. Bye, everybody.
Thank you, Mike. Thanks.